All right, this mini lecture is on diffraction of light and what happens when light encounters an edge. Now, throughout history, there's been a debate on whether or not light behaves like a wave or light behaves like a particle. And various experiments have manifested that show both those properties. And we're going to talk about the property that shows that light behaves like a wave. Now, the idea, just to give you a little bit of that nomenclature and the vocabulary, the idea of light behaving as both a wave and a particle is what we know as the wave-particle duality of light. So it is true that waves, in fact, behave like both. One of the first pieces of evidence that light, I keep saying that waves behave like both, that light behaves like both. One of the first pieces of evidence that light behaves like a wave is what we know today as diffraction. So this is when light hits a boundary. So if you imagine water waves, and the same is going to be true for light. We're going to use water waves to help you picture it clearly. If you imagine water waves coming up to like a bulkhead in a swimming pool that has an edge or an opening, or a protrusion, a cement dock protruding out into the lake, and a wave comes up and hits that dock, we notice that the wave sort of bends around the dock. It doesn't just stop when it hits the dock. The edge of that dock, it appears as though it bends around the dock and then continues on along the way. Its shape slightly changing, or the direction of its motion, I should say, slightly changing. So let's take kind of a picture representation of that. Imagine that we have a source of a wave. It's producing wave fronts traveling out. So the wave is traveling in that direction. It's producing a variety of wave fronts, moving out. So the wave crests are moving in this direction. All right, then we hit that dock that's protruding out into the lake. Okay, so here's that barrier, and that barrier has this edge right here. So I'm going to zoom into that edge. So we're looking at a point where as the wave hits that barrier's edge, we're right at a point on the wave where, like, essentially those wave fronts are going to be just parallel like this. Okay, so we're zooming way, way in, and here's the edge. Right, so there's the edge. Make it nice and thick to kind of give that representation. What do we see just on the opposite side, just as the wave hits that edge and tries to travel further? Well, we see this sort of curving around the edge, right? When a wave hits a cement dock, we see that wave kind of on the other side of the dock, kind of progressing forward. So let's now imagine that we take two docks and we put them across from each other. Okay, so we're zoomed in pretty much a lot. Again, we're zoomed pretty far in. So here's our wave front. It looks pretty flat as it hits that barrier. We're right close to the front edge of that wave front, for example. You might imagine that it's going to curve around the dock in this direction too. So we get these sort of curvatures around the dock edges, and then the wave proceeds further. Now let's shrink that even more. Okay, if we shrink that spacing even more, so it's a very tiny spacing, we notice significant effects. The wave comes in, and we notice that the wave then seems to curve completely around and open up into that space beyond. This is the idea of diffraction. This is what we mean by diffraction, this kind of curving around the edge of these boundaries. Now, this was first observed in a very cool experiment, Young's double slit experiment. And this was really, like I said, one of the first evidence, of the wave nature of light. And what happened in this is the prediction, if light traveled as a particle, didn't match what we observed. So let's imagine that we have a screen with two very tiny slits, very, very small. These are even smaller than pinholes. And far far away from that, so a large distance, we place a screen. All right, so this is pretty far away. And we present this with a source of light. So we have light. If light, and that light, you can just imagine it just shining on this area. If light was indeed a particle, we would see two tiny little bright spots on the other side. So if it were a particle, we would see tiny bright spots on the other side on that screen, because only the particle that traveled through the slit would hit the light. But that's not what we see at all. Actually, what we see is, if I look at this screen, I see multiple bands of light. In our double slit experiment, we see multiple bands. Multiple bands of light are appearing on that screen, yet only two spots can open up, or open, on the barrier. This was the first evidence that this idea of diffraction was happening, and like waves in the water, that must mean that the light is bending around these edges and hitting the screen at multiple places. So this was a pretty phenomenal experiment that showed evidence that light behaves like a wave. Let's talk about how that actually happens. So here we have this double slit experiment. I'll go ahead and erase this. I'm going to go into more detail specifically about diffraction in another video, but just to give you an idea, here is the wave coming into these slits, and now that wave is moving off. I'm going to use a different color. It's moving off in these two new wave-like patterns as it emerges on the other side. And we can see, based on what you've learned in the past about constructive and destructive interference of sound waves, for example, that these waves are going to interact with each other as they move towards that screen, and they're going to constructively and destructively interfere. And it's that constructive and destructive interference that gives rise to the bands. Where there is light, constructive interference is happening, whereas darkness, destructive interference is happening. And this would only occur if light was in fact interacting in the phenomenon of a wave. All right, so check out the next video more specifically on details of diffraction and how we actually measure where these light beams appear. Good job.